All right, so we already have seen how to destroy concrete and stuff like that and shatter glass. Now in this example, we want to destroy wood. And for this, I took this black pearl model here. Don't get too excited. We will not destroy the whole ship because it would take too long for what I want to show you. So I separated just what I wanted, and that is a single mass. And here's Tommy. And as usual, when I brought in any kind of geometry from outside, it first gets scaled, then I convert it, and then in this case, I blasted away the mast here for our example. Now what we want to do is we want to shoot a projectile, a cannonball, through this so that it breaks apart, and I will not use the RBD material fracture here to turn this into wood, because as you've seen, I'm not super happy with the way this system creates the elements. It usually doesn't look that good in my experience, and especially it is very hard to control and very slow. So we'll go with the old school way of turning this into splinters basically. And actually let's start with that right away. The first thing, as you remember, I do is I just transform this thing down by 1/10. So I scale it in Y for now in 2.1. And Tommy is actually already done here. And we could turn this now into a volume and then scatter inside. That's perfectly fine, but I'm a bit too lazy for that. I just use a points from volume directly. And of course you can see they are in the grid, the points right now. We don't want that, so let's increase the jitter scale. And now let's check how many points we have. 290 is way too low, of course. So let's play around with the point separation a little bit. And now we get 2,300. That's maybe a bit too many. 800, 900 is too few. So somewhere in the middle, 0.6. Yeah, so 1,300 points seems like a good idea. And then let's use a Voronoi fracture to break our mast apart. And of course, I have to use the transformed version. There you go. And of course, the trick now is to scale it back up afterwards. So we take the first transform and invert it. And for this, we just press Ctrl, Shift, and Alt to create a clone of it, which means every parameter is connected with it. And the only parameter that we don't want to be connected is this one, the invert transformation. So let's break this with delete channels because we want to turn it on. So it does the complete opposite of what the first one is doing. What I usually do to make this clear that they are connected is I just give both the same color. Let's choose a green, for example. And now we have here our mast split up. Let's use an exploded view to have a look at it for now. Of course, we can always change it later if the numbers aren't good or anything, but here you can see we have those splinters. I think they're not long enough for my taste, so let's increase actually the scaling. So 1/10 is usually not enough, so let's turn it to 0.005, and then of course our transform 2 will do the complete opposite. And I think now they start to look a bit more like bigger splinters. So I think it's actually not too bad. Maybe a few more points wouldn't hurt. Yeah. For now, I think that's not too bad. Let's see how it looks. If it doesn't look right, we can always change it. But at this point, I would actually already think a little bit about optimization. Because what we have here right now is we split up the whole mast in its whole length into splinters. But if I look at my, and I've already prepared that, projectile, let's take one of the two. There it is. This will be our cannonball that will fly into this thing. You can see the area it hits is relatively small compared to the rest. And this, of course, is where the main destruction will happening. So what I can do is I do a little trick. I will only make sure that the main points at least are in this area. And I can do this by simply using a Boolean to cut away this area where my impact will be. So with a Boolean and a simple box, I can make sure that only here will be the area I want. I use the Boolean, by the way, so that the top and bottom will be closed, because then the points from volume will still work. And it then looks like this, but what I want is only the intersection. There you go. So, you know, of course you can give it a little bit more area, obviously. But then this only area will be broken up, and you can see now that the whole amount of points, or the main amount of pieces, will be there. Now, of course, what you might be wondering now, wait a minute, now we lost all the rest of the mast. We still need the mast, right? Well, what we do now is simply we take this version of our mask, the shorter one, to create our points. There they are. So including scaling it actually. But we will Voronoi the whole mast like this. But of course, be careful when you scale even the small bit here compared to the whole mast, you still have to scale the original mast, right? So what we can do again here, again with Control, Shift and Alt, we copy that thing over so that we have a scaled version of that mast. And this is now the cut-off piece, which we will actually Voronoi and then scale back up. The advantage of this is, as you might be able to see, that the main detail is down here. Maybe we can visualize this as well in the Voronoi fracture with the name attribute or the piece naming here. There you go. And then up here we still have some breaking up, but it's way less because the points that the Voronoi is using are concentrated down here. And this is often a very good idea to, not Voronoi everything or break up everything the same amount, but concentrate on the areas you actually care about. And especially when you look in comparison what the whole mask looks like and what the area is that we actually mainly concentrate on, you can see this in this case saves a lot of computation time later on. So I hope that makes sense. We basically combined two techniques here. We scaled the thing down and back up after the fracturing so that we get splinters. And on top, we actually use a different, smaller part of our simulation geometry to concentrate the points in this area. And then we fracture based on that. And this way we have the most pieces in the impact area. Of course, the disadvantage is that we have really long splinters up here now because they're all based on the points down here. So if you wanted, you can add additional points here to break this up a bit more. But for our case, I think this is fine. I just wanted to show you that you can define where the points of your Voronoi should be. Now, the rest from here is relatively straightforward. Let's put this finally into an RBD bullet solver. And let's first see how our pieces are actually behaving. So let's turn off the visualizer. And of course, when I press start now, the whole thing will just fall down, obviously. So let's make sure that we have a ground plane. And let's see what we get. And it doesn't look too bad. The whole mast is falling apart. And we can now see how big our splinters are, which looks interesting, which is not what we want for now. But of course, we will glue them together in a second. What I do want to have though is the pieces are a bit too big for my taste. So let's quickly increase in the points from volume the amount of points a bit more by lowering the resolution or by lowering the point separation. And yeah, around 1200 is what I'm aiming for. It's 1500 now. So let's now see again how the detail is. It's a good bit slower now, but yeah, I think this is not too bad in terms of amount of detail that we will potentially get out of this. So let's now make sure that we actually let this not happen, because that's not how a mast usually works. So let's use constraints to glue the whole thing together. We already have our constraints here coming from the Voronoi fracture, so let's connect them. And as we know, it will not work. It complains because what's missing is the RBD constraint properties, so that it actually knows what kind of constraint is on it. So now it's set to glue, and let's leave the strength at 10,000 for now, and let's see what happens. And hopefully nothing should happen. Okay, it falls down a little bit and then it stays intact and wiggles around a little bit. But yeah, it seems to work, so our constraints are working. Now at this point you might think, great, so moving on, be careful. There is something you have to take into account here. We would have noticed this later on, but I want to fix it now. Remember, this Voronoi fracture gives us the constraints based on this state. So those are the constraints, and then we scale our geometry up, but those are still our constraints, as you can see down here. So the constraints, even though we know that it doesn't matter where they are in space, they are way too short. And what that means is that those pieces have a shorter rest length when they start. We can actually check this. There's our rest length. And this is still relative to this size originally. So basically what's happening here is that the rest length is too short. So all the pieces when you start are pulling on each other. So basically, if the pieces are that far away, the constraint only has a rest length of this length, and this means the two pieces will constantly pull on each other, and there is some kind of energy inside of the system. This is not a good idea because it will influence the way your simulation behaves, and this is why we have to fix this. So what we need to do is we have to scale the constraints by the same amount we scale our transform to. So again, what we can do is we just copy that thing as a clone, and you can see now it's scaled up. Now the problem is it seems to be correct, but it isn't, because if you look at the rest length and you can just turn the transform on and off, it's still the same, because it's not really about the length of the constraints in the viewport, it's about this rest length attribute. So a transform alone is not enough. What you could have done instead is you could completely ignore this and just use a prim wrangle and multiply it with your scaling multiplier. Or the way I do it is I just take the same transform and then just use a measure node to simply recalculate the rest length. And what we want to measure here is, for the primitive, the parameter or length. And by default, this will create a new attribute with the right number called parameter. And we want to rename that attribute, there it is, and call it rest length, so that it overwrites the wrong rest length, and now we have the right rest length again. So again, you could just scale that number yourself, but I find it better to just use the same transform and then remeasure it. I feel that's a bit safer, because anything I change here will automatically result in a correct new calculation. So let's double check if still everything works. Yeah, and at least, you know, nothing explodes, which for now is a good sign. So let's finally bring in all the other elements that we already talked about, and at this point is pretty straightforward. First of all, let's finally bring in our projectile. The way I do it here, we talked about this before, you have two options basically. You either take a sphere that is an active object with a start velocity and then let the two interact with each other, which has the advantage that the sphere will react to the impact and will slow down. The alternative is to animate the sphere by hand and use it as a static object, which means it will not be influenced by the simulation itself. It will just follow its animation blindly, which makes sense for very fast or strong projectiles like a cannonball, because then you can make sure that you only have to care about the active object, because the collision object will always follow its path. So in this case, this is what I want to do, and I prepared this animation already. There's our sphere moving along, hand animated, and we want to put it into the collision. And I just realized that my frame range is starting at 1. Let's quickly fix that. That's a bit annoying, but it might be helpful to see how to do that. Of course, first of all, we change the global animation frame range, and we start at 1001. And then instantly it will start to simulate, because our solver, our RBD bullet solver, is starting at 1. So let's change this to 1001. And of course, with escape, I was able to just stop the simulation. And then the sphere has still the old animation on it. So with Shift, I click on the parameter and get the animation editor. With H, I can show the animation curves. And then I just select the first points, change the frame of those, and then the last points and change the frame of those. And now the animation is moved by 1000 frames. So let's now run this and see what happens. Yep, and first of all, there was a template flying by. Where is our projectile? Oh, it's still over there. And it's not moving. Why is that? Of course, we know why. We have to handle collisions, and under collisions, we could change the collision type to deforming, which would work, but it's not very efficient. So let's do it better. We take the movement that we have and turn it into an animated version. And we can do this with the RBD deforming to animated, which has the nice effect of packing our geometry as well. Oh, but we need a name attribute for our sphere. All right, we can do that. How about calling it projectile? There you go. And now let's turn the node on and off. Okay, now it works. And we still have our movement in it, but now it's actually an animated movement. So let's see if that works now. Let's reset the simulation and press start. And yes, our projectile is moving and it hits our mast and the mast flies away and then breaks apart at the top, which is not what we want. But well, obviously there's something wrong in the first place, and that is that our mast just flies away. And we know why, because we don't have any connection to the ground, no foundation. So let's quickly do this. We know how to do it. We need to deactivate the lower parts. So what we have is currently actually an unpacked mast. So let's fix that first. And we will use an assemble node. Thankfully, the name attribute already comes from our Voronoi fracture. So we do not need to create that, but we want to pack our splinters. So now we have a packed version of our mast. So let's now, if we want to deactivate stuff, first make sure that we activate everything, because otherwise the active attribute will be 0 by default. So we activate everything. Let's be clean this time. Let's call it active1. Then we create a group. Let's make sure this is a point group. Let's call this active group or something like that. Actually, it's a deactivation group, but it doesn't matter. So we use a bounding box. And yeah, that's actually not too bad. It's a bit hard to see what pieces are used, but I think like that is quite all right. And we use that now. Let's copy the active1 node, call it active0, because everything in that group we want to deactivate. So let's see if that worked. Theoretically, the lower part should now be tied to the ground. And if I run this, you can see nothing happens anymore. And this is a bit weird. And to be honest, I can't explain to you why it worked before, but there is a reason why it doesn't work now. Because when you look at the frames, interesting enough, and of course that's on purpose, the projectile never actually hits our mast. What this means is that currently simply there is no frame where the bullet solver recognizes a collision. Again, I'm not sure why this worked before, but it definitely doesn't work now. So how can we solve this? Simple, we just increase the substeps that the bullet solver is seeing. And just to be clear, under setup, we have the bullet substeps. Those are the internal calculation substeps. But what we need to change are the global substeps so that the incoming geometry from outside will be recognized between the frames. Now, thankfully, just to double check, we actually have substeps here. If we want to use substeps from the collision objects, we have to make sure they exist. For example, we could do this in the global animation by turning off integer frame values. And now with my arrow keys, I can check if there are subframes and they exist. So this is good. Let's go back to the integer version. And now we want to use the global substeps to, let's say, 3. I think that's a safe bet. And when we run this now, okay, that's a good sign. And there we go. In the moment we should get a reaction, we get quite a lot of it. Let's have a look at it from another angle because it's a very nice effect. And there you go. Looks really nice. So here's the full sequence currently. And then the mast falls down. And okay, now we can see our splinters at the top. We could, adjust this a little bit. All kinds of things we can do now. You could play around with this. One thing I would try here is maybe to increase the glue strength so that when it hits the ground, the pieces are not falling apart. Of course, we could even adjust the strength based on the height and all kinds of things. Maybe a little practice you could try for yourself. Yeah, so here, as you can see, this worked pretty well. Now the mast is not breaking apart on impact. Even though that might be something you want, then you might also be able to adjust the fracturing. Of course, there are all kinds of other things you could adjust, play around with the scene however you want. To finish this, let's maybe give our wood a little bit of a wooden color at least. I kind of forgot about that. Let's look at it from the outside so that we don't see the constraints. Let's maybe merge it with our projectile that we turn black, let's say. And let's finish with that. So here is the result, and I especially like, just before we finish this, to kind of fly with the camera around this as if it was frozen in time. That always looks really cool. So maybe a way of rendering this whole thing, stopping it at some point. But anyway, this is a flipbook of the whole thing. This is one of my favorite examples in the whole course. So hope this is helpful. Thanks very much and see you later. Cheers.